nanoHUB.org.
Online simulation and more for nanotechnology.
All right, so we proceed, and for the next 3 lectures we would consider some challenges and perspectives in the area of quantum. As I mentioned, I guess it's nobody, or at least very few people would argue with this, that the next technology evolution is going to be quantum. There are, of course, lots of new opportunities and lots of new challenges. So it's going to be like in the Matrix movie, but maybe going in many aspects beyond of that. So it's really an exciting area. So there are many these famous many different presentations of this famous Moore's law. And this is actually one of them, which shows how not the number of elements increases with time. That's the most famous probably way to show it. But this shows how the number of atoms needed per 1 bit decreases with time. And you could see that actually the prediction is, although it's what people are already trying to do, that around our time, we need only 1 single atom per bit. So that's, of course, means that new challenges are coming, meaning that you have to really use the laws of quantum physics to describe what's going on. But also there are new opportunities which are not available in the way of classical systems. And the key such opportunity is actually what we call quantum superposition or entanglement. That's a truly quantum phenomenon which eventually enables what we call quantum speed up, when you could process information in a parallel fashion because you don't have anymore this simple situation 0 or 1 bits, but you have much larger information space, anything between 0 and 1. And that's what could be supported by this quantum superposition. Well, in that regard, if we now recall that photons is the ultimate unit of information, because with photons we package information into a signal of 0 mass and propagate it at the ultimate speed of light. We probably would like to use photons as carriers of information, and that's, I would say, prevailing approach nowadays, although not the only one. And in terms of units which you use for information to record and process it, we would like to go as small as possible, and that brings us to this level of single atoms. So indeed, very exciting opportunities with lots of challenges, but also with a huge promise and potentially truly dramatic impact on industry in our everyday life. So in principle, there is almost all components have been demonstrated or at least thought through needed for what we call quantum computing. This is one of the way to go. In this case, that work done by Chris Monroe at Joint Quantum Institute. This is a cover one of recent science papers. And in this approach, you use trapped ions to create this entangled quantum superposition. And in principle, it's not impossible. It's certainly one of the way to go. The challenge, though, if we admit that we would like to have our new technology being chip-based, like what we have in the case of electronics, so basically on-chip, and also being able to operate at room temperature, which is, of course, for many applications, we would like to our computers or whatever systems to be able to operate at room temperatures, that this approach might face really serious challenges. So if you kind of narrow down all possible approaches to those which satisfy this criteria, room temperature and being on chip. And although I should say again, not everyone pursues this direction, but if you're pragmatic and would like to really use it everywhere under any condition, that's might be the important requirement. So and if you look at the existing approaches and separate them in, well, what needed actually 2 different important components. One which would enable this memory qubit gate. And here I list different approaches, ranging from photon to superconducting units, single ions, I already mentioned, atoms, quantum dots, topological qubits, color centers. That's different groups pursue all these different material units that potentially could be used for memory, qubit, and gates. In terms of information channels, so basically information carrier, you could use different, again, systems, ranging from dielectric waveguide to transmission line, free space optics, electrical wires, and nanophotonic waveguides. Nanophotonic waveguides, it would be like silicon waveguide, for example. And if you now look at those which satisfy both requirements, being able to operate at room temperature and scalable and being able to be used on chip, that actually there are only two satisfy this criteria. The one which uses photon and dielectric waveguide, and the other one which is using the color centers and nanophotonic waveguide. And as a result, we would pay more attention to these particular approaches. Having this said, it doesn't mean that other approaches wouldn't be useful. They're also very important, not only in terms of understanding, but also they could find a very important niche for their applications. Although, if you think something which would replace our classical computers, the requirements being able to operate at room temperature and on chip are indeed very important. So this is a kind of roadmap which we could envision for this integrating quantum information systems. And I should say that there is lots of progress in this regard already has been accomplished. So you could think of various elementary components of future computing. And that, of course, includes things like waveguides, single photon sources, detectors, that's all important. And again, there are demonstrations of all these single components already. In terms of devices, or let's say more higher level components of quantum computing, these quantum registers, quantum gates, and quantum channels, of course, are critical ingredients. And again, there are several demonstrations of that. Even in terms of quantum information system architecture, like how the system should work, and in terms of this quantum information algorithm and error corrections, there is already lots of progress, lots of demonstrations. In some cases rudimentary, in some cases pretty much advanced. However, the important question to ask, and what I say now maybe not necessarily everybody would agree, but that's at least our vision, that it's really critical to think of a material platform for future quantum photonics, or in general, let's say, quantum circuitry. So if you recall what happened to electronics, I mean, basically silicon made a difference. So it's really important that you have right materials which would enable all this platform for electronics. And now we should think of something similar, what would play in such a role in terms of material platform for quantum photonics. I already mentioned for classical nanophotonics, that's the biggest challenge, because almost all these plasmonic components which enable this focusing light down to nanoscale until recently were used based on silver and gold, and those materials have serious problems in terms of being used on chip. And so in that particular case, in the case of plasmonic nanophotonic, there is tremendous progress in terms of developing new material platforms. So for quantum photonics, we're actually in the very beginning. It's absolutely not clear what would be, let's say, silicon for quantum photonics. What would play such an important role? And importantly, it might be not a single material. It's hard to imagine that any existing single material would satisfy all the criteria. It probably will be a hybrid system. But how it's going to look like, that's a big question. And we should not be naive. We probably should require that it should be CMOS compatible, because this is an existing industry with hundreds and hundreds of billions of dollars invested into this field. And if you would like to really have this big scalable approach, so it's better be compatible with existing semiconductor industry, which is basically CMOS, being CMOS compatible. And what are the requirements for all these future material platforms? It should be very fast. It's indeed important. It should have very low losses, because this quantum superposition, it's extremely fragile property, if I could say so. And it's to keep this quantum coherence, it's really important to minimize losses. So it should be scalable in terms of production, and it should be also cheap. I mean, and because materials which you use and the way you make this system should be really cheap. So there are so many important criteria to satisfy. And it's a good idea when you think of various quantum approaches, quantum systems, to put this as a boundary condition, as constraints from the very beginning. So generally speaking, we would like to see future material platform for quantum photonics CMOS compatible and require and satisfy all these requirements needed to bring it to industry. So during these 3 lectures on quantum photonics, that's what I plan to cover. Today we will talk about current material platform, what people use, and then we will speak of some hybrid material approach, which I said, which would combine materials similar to those which used in nanophotonics, such as transition metal nitrides and transparent conducting oxides. And then we will look at perspective for quantum nanophotonic devices and cover some particular important aspects, such as single photon sources and quantum registers. And we always will be looking what potentially the field of plasmonics and metamaterials, what kind of role it could play, how it could enhance these quantum properties. Because the best things happen when you merge different fields. And since plasmonics metamaterials is a really truly advanced field of optics and material science now, it would be very good to look at the potential use of all this progress in this area for quantum system, for quantum technology. And in the end, I a little bit speculate how this quantum information system, integrated quantum information system would look like. All right, so, and today we focus on this currently pursued material platform, what people now are mainly playing with, trying to demonstrate various quantum properties. And there are several different directions to go. And of course, silicon is one of those. As my friend Jacob Kurgin likes to say, that there is no more silicon compatible material than silicon itself. So, of course, it would be very nice to use silicon for all these quantum applications. And that's actually pretty much an important direction pursued, for example, by O'Brien and Thompson in United Kingdom. So, of course, there is lots of activities in using 3.5 groups, quantum dots, quantum wells, and groups of these individuals like Peter Lodal in Copenhagen and other folks pursuing that directions. Diamond and color synthesis diamond lately became one of the most popular direction to go. And of course, other materials more traditional in a sense, such as lithium niobide, which is used for optoelectronics, that's yet another direction. So we wrote this relatively recently, this review, where we describe all these different approaches. My postdoc, Simeon, actually spent lots of time looking at what are the directions, what are the pros and cons for all of these directions. And we now briefly overview all these directions, indicating what are the advantages and what are the disadvantages with all this approach. And without probably selecting one single material which would fit all the sizes, because there is no such material. So, and that remains the problem, what would be the material platform of future of quantum photonics. So let's start with silicon-based platform. So of course there are a number of advantages, and the most important one, it is as CMOS compatible as it possibly could be. So there are, in terms of guiding information, you could use as a doped silica, basically something similar to what we have in optical fiber, or you could use silicon on insulator. In this case, the confinement is stronger. In both cases, of course, the confinement is defined by the diffraction limit, but because the refractive index in silicon is higher than in doped silica, you could accomplish stronger confinement. Remember that it's lambda over 2n, And since refractive index in silicon is quite high, like 4.5, so basically it's significant, like 3, well, it's more like 4, yeah, 3.5, 4. So it's significant confinement it could accomplish. Basically, the size of these guiding structures could be few hundred nanometers. So with silicon on its own, we have a stronger confinement. In terms of what already demonstrated for these quantum applications, it's single photon sources, which is very important. Of course, for quantum applications, you need to have a photon, a source of single photons, which you could then develop into entangled photons, pairs of entangled photons. So, but this is a key ingredient to generate single photons and deterministically, not stochastically from time to time, but deterministically. So it's also important that one could show this rudimentary photonic quantum processor, as has been shown by O'Brien in Bristol. In terms of advantages, they are listed here, is rather tight photon confinement, particularly if you use silicon on insulator. Strong Chi3 for all the switching operation, for making this gate type of operations, of course, you need high nonlinearities. And in silicon, the nonlinear response is rather high, although if it's used thermal phase modulation, that it's perhaps not as fast as it could be. And of course, as I pointed out, easy fabrication and integration with CMOS, that's a very important advantage. As for drawbacks, in silicon, there is 2 photon absorption, and that's important. So when we're talking about telecom 1.5, 2 photon absorption is a factor. The biggest problem of technology, if one could say this, silicon is material of choice for electronics, but it's indirect material. And for photonics, it's really not a good material. Because it's an indirect material, you do not have this like laser pump sources. So silicon, unfortunately, is not good for, in that regard, for efficient optical source. And 4-wave mixing, which is quite important in terms of basically wavelength division and multiplexing, the bandwidth is relatively small, so it's difficult to separate pump from signal in that regard. So there are, of course, some obvious pros, but there are also some cons as well. Also, it requires pretty large overhead. I mean, if you want to make CNOT gate, it would require to generate many pairs of photons. So there are some disadvantages as well, even though, of course, it's one of the very important directions to go and lots of exciting work done. I honestly should say that somehow in Europe there are more quantum activities, quantum photonics, quantum circuit activities than in this country, but we are trying to catch up. So like in this particular example, when it comes down to the silicon quantum photonics, it's almost entirely done in Europe, and specifically in Bristol School by O'Brien and Thompson. So those are the key players in this area. Related to this, silicon nitride, that's, of course, it's also a very good material. It has quite strong Chi3. It has high operational bandwidth, which is important. 2 photon absorption is somewhat lower compared to silicon, which is good news. It has low thermal expansion. Why it's important? Because to have this switching, nonlinear operation, you have to apply rather high intensities. When you apply high intensities, there is a thermal expansion. And if a thermal expansion is significant, you could actually destroy your structures because different elements would have different thermal expansion coefficients. You would create stress and destroy your structure. So it's important that it has low thermal expansion for these high intensity applications. So there are already demonstrated sources of tunable narrow band entangled photons. As narrowed as only 30 megahertz. Why you want to have it narrow? Because eventually you would like to generate indistinguishable photons. For quantum applications, it's very important that those photons which you generate, single photons, you generate deterministically, and they're also indistinguishable. They have exactly the same characteristics, the same phase. That's very critical for quantum applications. It is something still yet to accomplish. Like room temperature, source of single photons with high efficiency, which would generate indistinguishable photons. It's still not accomplished yet, I should say. So my group is working hard on to do this, but as well as the other groups as well. So, and very important advantage that you could, well, I should say that in general, many operations might be easier to do in visible or in the very near infrared. Sources are better. I mean, the nonlinearities quite often are better there. So there are many advantages to work in the visible. But in the end of the day, you need to have everything at 1.5 because there is no yet substitute, and probably people don't even try to do it, to send information over large distances in a different way than we do it now. And this is 1.5 optical fibers. So in the end of the day, you need to come back to 1.5. If for whatever other operation you switch to other frequency range, eventually you still need to go back to 1.5. Therefore, it's very important to convert whatever wavelengths you're working at back to telecom. And this, for example, has been demonstration using this 4-wave mixing type of, and in this case, they would convert 980 to 1550, which is also important. In terms of drawbacks for silicon nitride, nonlinearities are not as high as in silicon, it should be mentioned, and it's somewhat difficult to make reconfigurable circuits. Anyway, silicon nitride, and people like Alex Gaeta, who is currently in Columbia, moved from Cornell to Columbia, pursuing this direction, it's indeed very promising, and it's compatible with silicon. So I should say this is indeed a very promising direction to go, although it doesn't solve on itself all the problems. Diamond, I mentioned that's, at least lately, draws lots of activities. And in this particular area, I should say in this country, there are wonderful work done in group of Misha Lukin in Harvard, Mark Alankara in Harvard, George England in MIT. So pretty good work, lots of good work done in using all type of color centers in diamond for various quantum photonics applications. So in terms of pluses, this is a material which has tremendously high band gap, meaning it's transparent, invisible, completely transparent. This is a big advantage. No two-photon absorption at all. So that's a huge and important fact. It has a very high refractive index, meaning that you could really have strong confinement, I mean, since your diffraction limited. So that's all big pros, and there are a family of available color centers. Diamonds are beautiful because of these color centers, and there are many of them. And there's lots of history, like how they observe these first color centers. Quite often they accidentally, by doing something, finding it, and then looking at their properties. So there are so many different color centers, and some of them good for one applications, but not good for others. And people still trying to find the optimal color center. But at least there is a variety of those to choose from, or to optimize them. That's kind of important. Well, and also things like on-chip Raman laser, which has been demonstrated for diamond, and that's could be important because that's a way to go from one wavelength to another one, as well as this frequency comb generation. The main challenge, you actually obtain the structure by using high pressure and high temperature multi-step procedure. It's expensive and not a cheap and not easy process. And most importantly, it's really difficult to integrate with electronics. So in the end of the day, as I said, we expect having some hybrid systems which would use elements of electronics. And how to integrate this tough hot material diamond with electronics, it's a challenge. Well, even though there are so many beautiful quantum demonstrations have been done with diamond. I should say in general that's quite common way when which science develops. You first demonstrate this beautiful phenomena, physics and so on. But at some time, and the sooner the better, you should ask yourself whether it would result eventually in real life applications. And for that, you should introduce, the sooner the better, these constraints dictated by real life industry. So in that regard, I mean, if you would like to choose what system to work with, you might want to think from the very beginning. So, but speaking of nitrogen vacancy in diamond, I should say there's many beautiful applications demonstrated. For the same reason why it's very hard to keep this quantum superposition, this entangled state. It's extremely sensitive to any environment. Any decoherent source and you would break this quantum superposition. But for the same reason, for exactly that reason, it's extremely sensitive to environment, meaning that you could develop sensors with record high sensitivity. And that's exactly what has been demonstrated. Basically, the biggest problem of quantum science or quantum photonics, which is very high sensitivity to the environment, has been used to develop fantastic sensors. And that's already existing technology. So quantum sensors beat all classical ones in many regards. And what I'm showing here, that basically by using these nitrogen vacancies, it has been demonstrated that you could have record high sensitivity in terms of in terms of detecting magnetic field, the lowest possible. And people now are developing magnetometers based on these nitrogen vacancies. The smallest electrical field, it turns out this is fantastic, shows fantastic sensitivity in terms of temperature detection, change in temperatures. All this, not speaking of more general ones, of course, that's what people are pursuing, like gates, qubits, single photon channels. But in terms of sensors, that has been already demonstrated. So nitrogen vacancy in that regard is a really promising way to go. What is really good about this nitrogen vacancy, it's actually a very simple fact that it has very long spin coherence time. Because the idea that you would use as a qubit, that's as a unit where you place your information, is spin degree of freedom. And it's important that it would have relatively long coherence time, ideally at room temperature. And in the case of nitrogen vacancy, it's actually the spin coherence time is rather long, actually up to 100 microseconds at room temperature. And this is a long time. Within this long time, you could do lots of operation and then save it in some longer living degree of freedom. For example, using electron spin, you could convert it to nuclear spin, which lives really long time. So, but it's important that you do lots of operations so that relatively long coherence time for spin degree of freedom at room temperature. And that, in that regard, nitrogen vacancy stands out. So this, the color center, which has really long coherence time. And the important thing, you could actually write and read it optically. So basically with photons, you could recode this spin degree of freedom. That's what I'm going to speak about later. So that you could make this spin register. You would basically by using light, you record this spin degree of freedom and then read it out. That's really important. That in principle all could be done with nitrogen vacancy. And the key thing is long coherence time. And in terms of compatibility, as I pointed out, if you use diamond platform, it's a bit difficult to use it, to integrate it with electronics. Like if you take single crystal diamond, how to combine it with electronics components? It's difficult. You could go other way. You could use nanodiamonds and place them on your chip. And that's one of the directions which some choose to go, including our group. Basically, you take a nanodiamond and place it, like in this case, in nanocavity formed by this photonic crystal. And you could do it by different ways. Let's say one of the most straightforward ways by using AFM tip. This is really difficult way to do it, but it's possible. And actually, in our group, we developed by far more efficient way. By using actually some kind of optofluidics, when you, in scalable way, could place many diamond centers in any position, in prescribed position with nanometer scale resolution. So, but the point that we can now, with nanoscale precision, place these nanodiamonds in the right positions in on your chip. But again, this is the most important advantage of diamond. As I pointed out, there are many color centers, and people like, first there was lots of work on nitrogen vacancies. Then Misha Lukin from Harvard, who is one of prominent figures in this field, would show that in silicon, actually, you have much more narrow line. This is actually the fluorescence line for photoluminescence line for nitrogen vacancy. It's broad, actually. And this is so-called zero phonon line, which is relatively narrow, but at room temperature it's not well pronounced. In silicon and in contrast, it's quite narrow. And having a narrow photoluminescence light is important to generate these indistinguishable photons. Because within decoherence time, and the more narrow width, the longer coherence time, you should generate several photons so that then they would have the same characteristics. So in the more narrow line, the larger coherence time, and the more indistinguishable photons you would be able to generate. So it's important to have it narrow. And the reason why in nitrogen vacancy it's broad and in silicon it's narrow, it's because in nitrogen actually it doesn't have center of symmetry. So, and therefore it meant that it would be very sensitive to local position. And since local electrical fields are different in different positions, you could have all this shift in the photoluminescence, spectral shift so-called. Whereas silicon does have a center of symmetry, and as a result, it's not sensitive to these fluctuations in the local electrical field. So, and one way or another, the line is much more narrow. People looking at other vacancies such as nickel, chromium, germanium. In many cases, you have exceptionally narrow lines. But the challenge is that as opposed to nitrogen, the spin coherence time is very short. In some cases, actually, it was not even demonstrated that you could optically detect this magnetic resonance, or DMR, optically detected magnetic resonance. And if you see a relatively long coherence time, then only at low temperatures. And as I said, in nitrogen, in contrast, we have long-living coherence time even at room temperature. To obtain something like that for other color centers, which have this advantage of having very narrow spectral line, but unfortunately no long coherence time for spin degree of freedom at room temperature. And that's the challenge. So people keep looking at some kind of ideal vacancies, but they're trying to do now a more intelligent way, perhaps to design this color center, which would require all the needed, which would have all the needed requirements. So in terms of these nitrogen vacancies, there are a number of, I mentioned already, there are beautiful demonstrations for various sensing applications, but also it has been already demonstration room temperature entanglement of proximal nitrogen vacancies in by this group in Stuttgart. So they basically do this what's so-called tomography of density matrix and show that there is indeed entangled states between these proximal nitrogen vacancies. So quite impressive result actually. I mentioned that there are people started to look at more intelligent way to develop color centers in diamond with the required properties. And Phil Hammer from Texas A&M University is one of the leading figures in that effort. By the way, I should say, to the best of my knowledge, Phil Hammer was the one who brought attention to the fact that diamond could be a very good material for quantum applications a while ago, actually. So what he is suggesting is actually to use something like diamondoid molecule, and by using high pressure, high temperature growth to create this fluorescent nanodiamond with required properties. So basically you build up your color center, and then you could actually place them in an array by using, for example, some kind of polymer. So in this case, you use diamond seed to get near deterministic array of nitrogen vacancies. So this is, of course, by far more intelligent way, but this still work is in progress. To develop this color center, which would have ideally long coherence time for spin degree of freedom at room temperature. So you could use it as basically a qubit to record your information. And very narrow photoluminescence line, so that potentially you could have a source of single photons, indistinguishable single photons at room temperature. So ideally you would write and read these qubits by using spin degree of freedom, and you would have also a source of this indistinguishable single photons at room temperature. So, and unfortunately, so far it has not been demonstrated for single color center. You, like in the case of nitrogen vacancy, you do have this long living coherence time for spin degree of freedom at room temperature, but very broad photoluminescence line. In the case of like silicon or germanium, you have very narrow spectral line, which could potentially be used to demonstrate room temperature source of single photons, indistinguishable single photons, and our and other groups working now on this. But in terms of the coherence time of spin degree of freedom at room temperature, it's very short. So we're still looking. So it's still an open challenge to accomplish. So yet another platform which some other groups actually pursuing, it's silicon carbide. Of course, also CMOS compatible. And in this case, you have some advantages. You could have this monolithic photonic fabrication, like making this type of structures like a waveguide with a resonator combined with a resonator, and it's all on this monolithic silicon carbide structure. It's important that you could have these bright color centers, basically a single photon source, which generate at pretty high rate single photons, 2 million counts per second. So, and color centers in this case would be silicon or carbide vacancies. So, and it results to generate this, to get these single photon sources rather bright with 2 million counts per second. It's a good source of single photons. In terms of challenges, it's difficult to isolate these color centers in silicon carbide. So basically, you randomly have it, you start working with them, but you would like to deterministically place your color center in any position you want to. And also, as for spin coherence, which I emphasize, it's so important, demonstrate it only at low temperatures. You would like to have long spin coherence time at room temperature. So losses are relatively low. It's high refractive index. It's very important. And also it can be doped, both P and N doped. So that's all advantages. But also there are some challenges. Those are the platforms which are largely currently used. And in addition to that, at least historically, most of quantum demonstration have been done with 3-5 semiconductors, such as the gallium arsenide and all type of similar modification. So, and that's of course very important. There is lots of progress here. I should mention that particularly most of demonstration have been done with quantum 3-5 quantum dots. But the biggest problem with quantum dots, which should be mentioned, they are non-uniform, meaning that that's also defined the position of photoluminescence lines. So they are not uniform. There is always this dispersion in sizes, and that's really poses a very difficult problem. Of course, positioning quantum dots, it's solvable, but challenging problem. And they largely work at low temperatures because actually otherwise the line are very broad. And because of the difference in size, it's already there is a shift in position. But to, like, for example, to have this at telecom, single photon source at room temperature, it's a very big challenge with quantum dots. So they typically work at low temperature, and it remains a big challenge to show room temperature operations for quantum dots. So losses are larger than in silicon, and it's also somewhat difficult to integrate with electronics. But even though it's possible by positioning them in the right positions. I also should mention some old friends used for lasing materials such as lithium niobide, periodically poled, and indium phosphide. In this case, you have large Chi2. You could use Pockels effect. So by applying voltage, so you could have control, you could do switching, and that also one of these interesting directions to go. So to sum up, I mean, we have all these different approaches, different material platforms which people pursuing now, and those include, of course, silicon and various versions of this, silicon nitride, silicon dioxide, 3,5, diamond, this lithium niobide. They all have certain pluses, all have some pros, but also some challenges. At least in my personal opinion, the future material platform would be hybrid, and probably will take advantage of this notion of this concept of metamaterials and plasmonics, because in the heart of the quantum applications is to have strong coupling and very strong confinement. Like, because you're dealing like single photons, to have strong effects, you have to have very strong confinement to realize the strong coupling. And plasmonics enables exceptionally small volumes. You could constantly bring it down to 5 nanometers, even though losses are relatively high. So you see there is a kind of a trade-off. With photonic cavities, photonic resonators, you have exceptionally high Q. Like these photonic crystal-based cavities, when you have a defect, Q could be tremendously high, tens of millions, really high Q. But volume is still diffraction limited. It's roughly wavelengths. With plasmonics, you could have exceptionally small sizes, 5 nanometers, meaning basically 100 times smaller than the size of a photonic cavity, and you're talking of volume, it's like million times benefit in terms of V. But Q is not as high. What eventually matters is Q over V in terms of this strong quantum coupling. So therefore, perhaps the right idea is to use some kind of hybrid approach. Plasmonics would realize small volumes, whereas photonics would realize large Q. And that's why I believe that future material platform would be somewhat hybrid, using the plasmonic materials, CMOS compatible, such as those I was talking about, and we'll be talking next lecture, and some ideas of photonic resonators.